Thank you very much, Alex, for this presentation. In the early 30s, the mathematician Otto Neugebauer and the Assyriologist François Thureau d'Angin published hundreds of cuneiform mathematical texts. Ever since, we have known that the history of mathematics did not begin in Greece in the 3rd century BC, but began more than 1,000 years before in Mesopotamia, Egypt, and perhaps other parts of the ancient world. The bulk of the known mathematical cuneiform sources dates from the Old Babylonian period, that is, the early 2nd millennium BC. At that time, an elaborate mathematics was produced by a few generations of scholars who belonged to the scribal school communities. One way or another, all mathematical cuneiform tablets are lists or tables. This fact reflects an important feature of scribal culture. Lists are omnipresent in cuneiform sources. Medical, astrological, astronomical, and mathematical texts, legal code, oral collections, and even some literary compositions are lists. From the very beginning of their education, scribes were trained to master lists. The study of lists is thus an essential component of our understanding of ancient Near Eastern intellectual history. Mathematical texts provide important examples which are particularly relevant, since they contain the most accomplished production of Mesopotamian scholars in the art of list making. But perhaps more important, the analysis of list structures provides access to mode of reasoning of the ancient mathematicians. Few rhetorical justifications are found in cuneiform texts. Does this lack of explanation and discussion in our sources mean that cuneiform mathematics was only concrete, practical, or empirical? Does it mean that the highly elaborated algorithms and procedures that we found in the texts were invented by chance or by trial and error? In fact, writing text fit into a complex world environment which included non-textual components such as memorized knowledge, calculation devices, and oral communication. Only part of these activities, the texts, reached us. And a great part of the ancient mathematical source remained lost. However, we do have ways to access, at least partially, to the manner in which the scribes reasoned. For example, the school tablets highlight some of the fundamental tools the ancient mathematicians used. Another method of investigation has been used recently with remarkable success by the historian of science Jens Høyrup. In order to illustrate this method, I'll take an example. This tablet, now kept in the British Museum, is one of the best-known mathematical cuneiform tablets, since it contains a veritable treatise on solving quadratic equation. Moreover, it's a typical mathematical cuneiform text. It contains a list of problems, each of them, as in most other mathematical texts, consists of 3 parts: a statement, a procedure for solving a problem, and the solution. This text provided Jens Høyrup with the most important evidence for his theory. According to him, the reasoning of the scribes was guided by geometrical representations, and these representations are perceptible in the academic terminology used in the text. His close reading led him to elaborate a literal translation which tries to express these geometrical references. The analysis of Europe is focused on the procedure, not on the list itself. My point is that the analysis of the list structure highlights other aspects of the ancient mathematical practices. In particular, the way in which some scribes try to generalize mathematical results. In order to point out some particularly significant aspects of the list structures, I will focus now on a single tablet containing a list. This tablet is a mathematical document from the Musée du Louvre that I have just published. I observe this object in all its material and textual aspects, that is, its name, its shape, its writing, its cuneiform, its content, its language, and so on. The object. The archives of the Louvre indicate that the tablet was inventoried in 1924. It belongs to a lot of 26 tablets which were purchased from the French dealer Elias Jéjou. Among these tablets, only 7 have been published to date. The majority of the published tablets are Old Babylonian and contain Sumerian literary texts. The other tablets of the lot are unpublished, but the database of the Louvre indicates that two are mathematical. The first one is the tablet discussed here, but there is also a second one numbered AO 9072. The second tablet is in many respects similar to the first one. I will return later to this point. Since the two tablets were bought from the antiquity markets, we have no archaeological information about their origin and their date. Returning to the first tablet, let us examine its material aspects. The tablet is quite small. It measures about 7 centimeters by 9 centimeters. It contains 3 columns on the obverse and 3 columns on the reverse. The writing is compact and cursive. Paleographical evidence shows that the tablet dates from the end of the Old Babylonian period, probably about the end of the 18th century. Some explanation about the language and the reading of cuneiform texts might be useful here. Most of the Old Babylonian texts are written in Akkadian, which was a spoken language in Mesopotamia during the second millennium BC. But a large number of scholarly and liturgical texts are written in Sumerian, which was a dead language in that time. Akkadian is written with a syllabic notation, and Sumerian is written with an ideographic notation. When we read the lines, from left to right and from top to bottom, and the successive columns are from left to right in the obverse and right to left on the reverse. So the end of the tablet is here. When the reading of the obverse is completed, the tablet is turned in an horizontal axis along the bottom edge. The lines are always filled. If a line contains few signs, large blank spaces are inserted, as we see here in line 3. The tablet is divided into sections separated by vertical and horizontal lines, and each section contains a mathematical problem. The shape of the tablet is significant since the typology of the tablets obeyed codified rules. These rules reflect specific practices of a community. All of the Old Babylonian mathematical tablets come from scribal schools. Remains of these schools are attested over a vast geographical area, and in the places where mathematical tablets were excavated by regular archaeological teams, school tablets were also found. Among mathematical tablets were found elementary school exercise, work of advanced students, as well as erudite texts. Different types of tablets correspond to these different types of activities. The relationship between some pedagogical activities and the type of tablets at the elementary level of the curriculum was underlined by Assyriologists for the Sumerian exercise. But the typology is exactly the same for the mathematical exercise. The typology of advanced and erudite tablets is not quite so clear. We can only say very generally that single-column tablets, namely type S, were used at the advanced level of education, and that multi-column tablets, namely type M, multi-column tablet, like this one, were used for teaching and communication between erudite scholars. To sum up, the typology of our Louvre tablet indicates that it was written by a scholar belonging to the scribal school community. Additional information is provided by a short notice written at the end of the text. This cuneiform reads as follows: 160 and 35 statement, it is the 7th tablet. The term imshu literally means hand tablet, that is a small round square or square school tablet. By extension, this term designates the content of the hand tablet, and by extension again, the content of a section. In mathematical texts, this term is used only in tablets containing statements of problem without the solution procedure. So, imshu can be translated here, statement. Our tablet contains 95 statements of problems. The cuneiform also indicates that the tablet is the 7th one. The presence of a rank indicates that the tablet belongs to a series, namely a sequence of several numbered tablets. 20 mathematical series tablets are known to date. 12 are kept at Yale University, 2 in Berlin, 2 in Chicago, and 2 in Paris. All of them, or almost all, have the following features. The list contains statements of problems without the solution procedure. Series texts are written with Sumerian ideograms only. A series tablet bears a cuneiform providing the number of statements and the rank of the tablet inside the series. Series tablets are always of type M, multi-column tablet. Some of these features are not common in the Old Babylonian mathematical documentation. This reflects the fact that writing a series text was a mathematical practice developed by a particular community of mathematicians and probably limited to a small circle of scholars. Now, let us look at the text itself. The first section reads as follows. The length and the width I added 15 linda. The length exceeds the width by 10 linda. Before going into more details, some explanations are necessary. Linda is a unit of length which represents about 6 meters. The indentation in the translation here is mine. The hierarchy of the items which appears in my translation does not appear in the cuneiform text. I will return later to this important point. The statements provide the relationship between a length and a width. No information is given about the concrete situations that these statements refer to. There is no question, no procedure, and no answer. But it's easy to guess that the length and the width are the dimensions of a rectangle, and that the implicit question is, what are the lengths and the widths? Section 1 provides two relations that can be translated into modern mathematical language by a system of two equations with two unknowns, as you see in the screen. It's an easy problem, well known by the scribe of that time. The solution is the length is 13 linda and the width is 20 linda. Section 2 contains only one relation. The other relation is missing. In fact, the other relation already has been given in the third section. So, section 2 refers to the following complete statement. The length and the width accumulated 15 linda. The length exceeds the width by 10 linda. This statement could be translated in modern language as shown in the screen. Sections 3, 4, 5, and 6 are written following the same principle. They contain only the second relation, and the first relation is the one given in section 1. These statements could be represented in modern language by these systems you see in the screen. As you see, the first equation is the same in the fourth system, always the same, and the second equation varies. The solution is always the same, 30 and 20. In section 7, the same elliptical writing is found, but the process is pushed one step further. We read 2 times, I repeated, I added. 36, 40. Information is missing. What is repeated, what is added? According to the principle we have just seen, the missing information is provided by the previous sections. What is repeated is the expression which is given in the first line of section 6. This is added to another expression given in the second line of section 6. And the first equation is given in section 1. After all the information has been collected in the relevant section, section 7 refers to the following complete statement expressed here in modern language. The solution is always the same, 30 and 20. In following section, the same implicit expressions are used and new equations are produced. Then these expressions are modified and new cycles of equations are produced. The process is expanded through the list using expressions more and more complex. For example, the text in section 59 reads as follows, as subtracted 45. After all the information has been collected in the relevant sections, section 59 refers to this complete statement here, expressed here in modern language. As we see, the formulation of the statement is highly elliptic. In fact, this statement is composed of 4 blocks. Only the 4th block is provided in section 59. The 3 other blocks were already used in the preceding statement and thus are not repeated in section 59. Block 1 has been given in section 35, block 2 has been given in section 50, and block 3 has been given in section 57. The reading of these extracts show the structure of the list and the mechanism used in order to produce the equations. In the same way as in section 59, each statement of the list is made of 4 blocks. The statements are produced by successive variations of the 4 blocks. Block 1 takes on several different values. Block 1, in fact, is the first equation, E1. For each value of block 1, block 2 takes on several different values. For each value of block 2, block 3 takes on several different values. For each value of block 3, block 4 takes on several different values. These variations produce a tree-structure list on which is grafted an elliptical repetition of the information. The information is given in each level of the tree and omitted in the following dependent level. This elliptical system of writing produces very concise statements. As we see, this text cannot be captured by a linear reading. The reader has to move back and forth in order to reconstruct the complete statements. How did the scribes identify the sections where they could find the relevant information? In the translation, I introduced indentations to help the modern reader. However, the cuneiform text does not show such visual aids. In fact, in this text, the most useful marks are the syntactic ones. As shown before, the statements are made up of 4 blocks. These blocks occupy different functions so they can be distinguished by means of lexical and grammatical indicators. Anyway, the readers of mathematical series needed some particular skill in order to use it. Until now, I focused on a single tablet, but our tablet belongs to a series. The second tablet from the Louvre, similar by its typology, its schematic, and its structure, probably belongs to the same series. Unfortunately, the colophon was destroyed and we do not know its rank. Among the known series tablets, 2 tablets from Yale are also similar to the Louvre ones by their content and by their typology. They bear the numbers 5 and 6. It's highly probable that these 4 tablets belong to the same series. If this hypothesis is correct, this group of 4 tablets forms the most complete mathematical series we know to date. As a conclusion, I would like to evoke some of the issues raised by the series texts. I will evoke only 3 questions. What is the language of the series? Since they contain no procedure for solution, what is their mathematical content? And for what purpose were the series written? Which scribal tradition did this very strange textual production belong to? First question, what is the language of the series? The issue is illustrated by these 2 different transcriptions of the same series text. The first transcription is written in Akkadian by Thureau d'Angin. The second is written in Sumerian by Neugebauer. As a rule, mathematical cuneiform texts are written in Akkadian, with a more or less important use of Sumerian ideogram. These isolated ideograms were probably read in Akkadian. But at the opposite, series texts are almost exclusively made up from Sumerian ideogram and contain very few Akkadian terms. Thureau d'Angin thought that the series texts were nonetheless read in Akkadian. Other scholars, such as Neugebauer, thought that the writing is purely symbolic. And the editor of Zeitschrift für Assyriologie, where I have just published the 2 tablets from the Louvre, thinks that the language of the series text is truly Sumerian. In fact, it's difficult to answer the question of the relationship between the series text and a possible spoken language, Akkadian or Sumerian. The texts used a highly specialized technical language, largely artificial. The verbalization of such a text, if indeed it existed, might be relatively flexible. The writing is perhaps more closely linked to a spoken language as are arithmetical notations or monetary symbols. The syntax used in these texts is in some respects quite different from the one used in other mathematical texts. It seems that the language was elaborated in order to express very complex equations with several hierarchical levels and embedded expressions. These features evoke what the linguist Zelig Harris called a scientific language. For him, the structure of each language of science is consistent with the structure of information in this science rather than the general grammar of the natural language. In this sense, the language of series text is a scientific language. Second question, what is the mathematical content of the series? As said before, the most distinctive characteristic of the series text is that they do not provide any indication about the procedure of solution of the problems. In fact, when looking at a statement such as the one given in section 59 of the tablet from the Louvre, this one could wonder if these problems were meant to be solved. We encounter this issue in other series texts. For example, in a series text kept at Yale, this one, we found many problems leading to equation of the 4th degree. They seem to be impossible to solve with known Old Babylonian methods, that is, procedure using geometrical representations such as the ones reconstructed by Jens Euler. However, my colleague, mathematician Steve Schneider, discovered recently that, rather surprisingly, some of them can be reduced to quadratic equations in a quite simple way. But in another series kept also at Yale, we found a statement dealing with the length and the width of a rectangle, as well as an unknown part of the length which has been subtracted and the remaining part of the length. The statement provides relations between these four unknowns, leading to an equation of the fifth degree. We know nowadays that no algebraic method of resolution exists for fifth-order problems. However, Steve has found that the apparently unsolvable fourth and fifth-degree problems can be solved with arithmetical methods if one restricts the set of possible solutions to regular number. As we see, it's not clear that the authors of the series text always know a procedure for solving the problems that they compose. The investigation of the author of these texts seems to be focused on not on solutions, but rather on mechanisms for producing and classifying problems. Third question, which scribal tradition did series texts belong to? The cultural context of mathematical series is not easy to grasp, since these tablets were acquired from the antiquity market and are of unknown date and origin. It's likely that the series date from the end of the Old Babylonian period and were written while the traditional Babylonian mathematics had already been fully developed. Evidence such as the structure of the cuneiform, the use of a highly artificial language, suggests that they could have come from the north of Mesopotamia. They could have been the work of community fleeing the destruction of the southern cities in the mid-18th century. Anyway, the series text appear to result from an original intellectual project quite different from the old southern tradition. In writing the series text, the scribes produced new mathematical material which represent a considerable extension of the mathematical repertoire developed in earlier periods. The interest of the scribes seemed to be no longer focused on the procedure but on the statements in an attempt to embrace the whole range of possibilities. This objective implied an improvement of technical writing, primarily a development of the syntax of operations, being based on the three structure lists and an elliptical system. The new syntax multiplies the potential of the previous one, allowing the notation of expression containing more than 5 hierarchical levels. The new writing techniques had made possible the notation of hundreds of statements, all concentrated on the limited space of small clay tablets. These observations suggest that the series texts are not some kind of textbook from which masters of the scribal school could extract the size. The fact that these texts were probably written in the context of scribal schools does not necessarily mean that they were written for educational purpose. These speculative texts seem rather to fit into a context of communication between erudite scholars. Thank you for your attention.